look, it's the name of my talk. I'm going to be talking about hacking data structures with math. Basically, it's how to use like the base version of programming languages to do some really cool stuff with data science and kind of bypass the necessity of having like neural networks and all the nonsense around that. So as you can probably imagine, I'm a data scientist. I work at a small consulting company called Data 317. It's been around for a little while. Worked with big, small companies in all kind of industries from the state to healthcare, worked a little bit at Springbuck, worked a little bit at Demand Jump before that. I'm a total math nerd, and probably the biggest thing, most important thing about this for this talk is I am not a Ruby programmer. So I primarily work in Python. And before that I was doing R, and I do a bunch of stuff in SQL too, but Ruby, as my Springbuck friends know, I pretty much avoided like the plague. But, you know, Miles said, oh, you don't really need to do Ruby stuff or anything like that. But I took that as a challenge. So we're going to do this hacking data structure stuff and data science using Ruby today through iRuby and all that good stuff. So we'll get to that in just a second. So before really starting out, one thing that I've learned the hard way with a lot of these talks is I have to define what data science is, just because it seems like everyone has different definitions of what that actually means. So data science to me, and what I'm going to be referencing, is the application of the scientific method and mathematical techniques to learn and understand data. So what that means is that we look at a data set, we look at the statistics that come out of it, we start trying to figure out if there's certain things that correspond to one another, and then we try and derive a formula from that. Sometimes that involves using neural networks, sometimes that involves using other methods for machine learning. Sometimes it is literally just figuring out that you need to pay attention to this one number over here and you can solve the problem that you're looking at. So probably the next question that comes from this when I talk about data science in general is, you know, what are the tools that you can use, or more importantly for this talk, how do you use Ruby in data science? This is especially relevant for Dan. I know that he's trying very hard to wrap some of the stuff around NumPy and building awesome visualizations and all that stuff. But, you know, as of right now, you don't. And it's kind of unfortunate because, you know, it doesn't have anything to do with the language itself. It doesn't have anything to do with the syntax. It doesn't have anything to do with design considerations or anything like that. It all has to come down to packages. NumPy is a big one. That's if I remember right, that's mostly what you're working on, right? In terms of extending that out and all that.
I'm using a different library that's replacing NumPy.
Okay.
More of a scikit-learn.
Yeah. Oh, awesome. Scikit-learn's another big one too. And at this point, Ruby really just doesn't have those packages, and that's why you don't see it used. Now, why is it that the data scientists are using Python? There's no good reason. It's just historical. I mean, the progression has been from S to R, maybe a little MATLAB, a little SAS, and now they've jumped into Python. There's really no good reason to it. There's no structural reasons or anything like that. So, you know, I would probably end the talk right now if, you know, I was one of those kind of guys, but nah. I wanted to actually learn Ruby and actually see what I could actually do with it. So, you know, one of the things that any programming language, anything that's true about true programming languages is, you know, you should be able to solve the problem no matter what. Who cares about packages? I mean, if you're trying to figure it out on the base case. And usually when you're trying to do this data science stuff in production, you have to code it up from base anyway, just because the packages that you're going to use aren't necessarily optimized for the problem that you're solving. So essentially, if you know your stuff, it shouldn't matter. Ruby is just a programming language like any other, using many of the same data structures, and that's really playing tricks around with data structures and doing things kind of in a clever way is all that you need to do in order to be successful at data science. And what this necessitates then is just math hacking, or what I call math hacking. So math hacking is using math to bypass nonsense. So, you know, a pretty good example that I talk about a lot, I'm sure some of the Springbuck people have heard this, is like when I was asked by the state of Indiana to look for tax fraud. So I was working at KSMC at the time, and they brought us in, and they know that they have a tax fraud problem. And you know, when we initially went in there, they wanted me to learn all the tax law. I'm not that smart, and I wasn't ever going to read all the tax law and then come up with a bunch of if statements about how to actually solve it. So instead, the math hack that came from that is asking the question about what is fraud really. And what fraud really is, you know, people are making up numbers when they should just be putting in numbers from a system. It sounds pretty trivial, but this is actually really important. It turns out if you have numbers that come from a system, they follow a pattern called Benford's law. And what that law states is that 30% of the time, the numbers that you see on a tax return, if you're reporting an income or something like that, are going to start with a 1. 15% of the time, they're going to start with a 2. 7.5% of the time, they're going to start with a 3, and it's going to follow that pattern down. If you look at your credit card statements, it probably follows that rule as well. And when people are making up numbers, they don't follow that pattern at all. So you just look for the differences of that expected pattern. With that system right there, I found $22 million of tax fraud for the state of Indiana in a couple of hours. It took them about 8 months to do that with all the rules that they had developed. And all it was, the way that we did it was just by looking at the first digit of a couple numbers they put on their tax return and aggregating them by some variables. That was it. That's math hacking, and that's fun. So, you know, I did that in R. R is a crazy language in itself. We also moved it into SQL and did some modification in Python using some other stuff. But you know, this being a Ruby talk and everything like that, I decided, you know, I really want to write bad Ruby because I know nothing about the language whatsoever. And when you guys were talking before, it's like, oh boy, this is going to be a fun one, but you know, who cares? And I'm like, what would be a really hard problem that I've been told several times is impossible to do for whatever reason, and it's, let's build a search engine. So, let's, I'm going to actually exit out of the program here, and I'm going to use Jupyter Notebook because I have to cheat and use a little bit of Python stuff. And we're going to build a search engine using Ruby. And then we're going to see what we can use that search engine for, just beyond, you know, the general textbook stuff that you can find on Wikipedia. So let's start with like what I'm starting with. You know, it's what do I have? I have a CSV containing descriptions of movies. So it's about 30,000 movies. I have a title, the description, the year that came out, all that good stuff. What I want is a tool where you can type in anything and find a movie that it's related to, okay? And isn't there a gym for that? Probably, but again, I don't know anything about Ruby and I don't even know where to look, to be honest with you, so we're gonna code it from scratch. So here is, I'm gonna import that, bring it in. If you notice these puts that are at the bottom, I think this is a hiccup of, oh, crap. How do I make this work?
Mirror if you can.
Apparently I don't know how to use a computer either, so please forgive me.
None of us do.
Hey, look, I fixed it. Thank you.
That guy used to work at the Genius Bar.
Oh, really? Well, that worked out.
Twice this week.
Could you make that a little bigger?
Yeah. So what's the magic key for that? Is that Command Shift
Command
plus?
plus.
Command plus. Okay.
Awesome, thank you.
Awesome. Hey, look at that. Also learning how to use my Mac as well. So, yeah. So, isn't there a gym for that? Basically everything I just said right there on screen. So, I'm running this block. You'll notice that there's a puts at the bottom of it. The reason for that is just because of Jupyter Notebook, and I didn't want to mess with the settings. I just wanted to get the code in there and all that good stuff. So, all I've done there, I've read in the CSV. I've done some stuff to turn it into a hash, where it's title, the key is the title, and the value is the description itself. And we just kind of manipulated it. So let's take a look at what's actually inside of that hash. It looks like this. So if we look at Star Trek, we have our title there. And then we have this big old description. All of these were scraped from Wikipedia. So,
We need a little bit bigger.
yeah, sure. Command. Much better?
One more.
One more?
Fair.
Look okay? Okay. So this is what the hash is actually what it looks like, and so it's pretty basic stuff. If we go in here and do Jurassic Park, we're going to get Jurassic Park out of it. Get a whole big long description. You see these interesting tags that kind of fall in. I think their system was a little weird, but yeah. And just to check, yeah, we have about 32,000 movies in there, or a little more than that. So one thing that I do want to bring up about hashes, and this goes for Python dictionaries, so the same data structures, is that hashes are cool. They're key value stores. They're super duper efficient when you're accessing the keys. They're constant time lookup. It has no cost associated essentially with it except for that initial init that you're going through. And how it's working behind the scenes is that you're taking an arbitrary key and you're mapping it to a number, and that number corresponds to some memory as some location in memory. And so the computer knows exactly where to look at rather than doing any kind of indexing or anything like that. That's where the name actually comes from. Hashes are really, really, really powerful in the sense that you can kind of do a bunch of complicated mathematics from just looking at pairs between keys and values. And you're functionally doing, for math people here, inner products all the way across, but that's not really too important at this stage. So, just to kind of go into some of the ways that we're actually looking at that. Again, we have a hash that is composed of title to description, but how would we actually search this, like if we wanted to find an arbitrary movie, right? So there's a few possible ways to do this that various people have tried. And before you ask, yes, each one of these I have actually seen in my career before. One is you can make up all the things that you can type into a search box and link them to the right movies. Yes, people do try that. It's head scratching to say the least. Second, you can categorize movies so that you can find certain genres using expert movie watchers. Again, you would have to categorize every movie and hopefully get your categorization right so that you could, go down the decision tree essentially in order to find that movie. And the last one is my favorite because I know all of you have worked in places where this is the case. We just want to apply machine learning and spend a whole lot of money to solve this problem. And that is never the answer. Basically, when people generically want to apply machine learning, you should run as quickly as possible because it's rarely the way to solve the problem right away. So to kind of focus on the problems with these, if you think about the first point there about making up all the things that you can type into a search box, think of how many variations that you would have to have. I mean, if you want to look up Star Trek, you could search, the starship named Enterprise, or Starship Enterprise, or the Starship Enterprise, or Enterprise, the starship, and think about all those variations. Now, you might say, oh, we can do some string matching, but wait a second, really? What if you just add another term on that or anything like that? The string matching is going to eventually fundamentally break down. If you try to categorize, well, again, Star Trek you can put into science fiction. But what if you want to search for the one with the whales? Now, how are you going to find that? I mean, it's not going to fit necessarily into science fiction. You're sure as hell not going to categorize it by whales, because that doesn't correspond to that category whatsoever. So how would you actually get in there? And then machine learning, I still scratch my head at that, to be honest with you. So I don't have a good example of that. It's just, you'll hear it. The best way to do it is to math hack this. And it's to ask yourself, what does it actually mean to search? When you type something into Google, what are you actually doing? You're describing what you're looking for, right? I mean, you're looking how to do that Ruby function. You're looking for that movie who has this actor in it. You're looking for some particular attribute of it. So, what you could do instead is compare description to description. So how you would do that, and I have a picture here just because I didn't want to skip ahead, or anything like that, is that you do an inverted index. And so what you would do is you would create a new hash that consists of descriptor words. And then you keep track of how often that word appears in individual movies. So you have this big long hash that has all the words that appears in those descriptions, and then the movies that they correspond to, with the counts being the final value. So it's a nested hash sort of thing. And we're going to cheat a little bit, but we really don't care about grammar words. So things like the, and a. If you think about it, they really don't give us a lot of information about what we're searching for. So we're going to exclude those. It just makes the math easier because the appears 6% of the time in the English language when you look at general corpus. You don't want to link across everything. So let's load that in. So in order to get this working, in order to create all the nice stuff so that we can create this inverted index, we get to this function. All it's going to do is going to lowercase things, and then it's only going to select things A to Z and then an apostrophe. And then we construct our inverted hash, which is a nested hash. I promise there's probably a better way of doing this, but again, I'm just doing it Pythonically. And I know that's a bad word, but forgive me. And then we let it run. This takes a little while. Part of the reason I suspect, and you guys can correct me if I'm wrong, is that I think the arrays inside Ruby are C arrays, and you have to define how large they are and all that good stuff. In Python, this is a little bit faster just because they're linked lists, and you can jump through them a little bit faster that way. And this didn't take this much time, but as it is when you're presenting, it takes more time when you're on stage. So there we go. So if we look at what this hash actually looks like now, if we look for dinosaur, we get a hash of movies and how many times dinosaur appeared in those movies. So Sherlock Holmes, it appears 3 times. The Lost World, it appears 1. Bringing Up Baby, it appears 1. So if we look up Starship. There we go, we have our Star Trek, so we're almost getting there, right? So the thing is that we want to do an arbitrary phrase. So what we're going to do is that we're going to take a query, we're going to split it up exactly like what we just did for our descriptions, and then we're going to merge all of the hashes that we get returned back, and that can be our score. And when we do our merge, we're very careful to make sure that we're adding the values in the hash and all that good stuff. So that's what this, I'm getting ahead of myself here, but that's what this function is doing. So we're going through there and we're just looking at the term frequency, or more specifically, the word count. So we create that function, and if we search by TF, we look at Captain Kirk. Now, right away, we do see some promising results, and I'm only grabbing the top 30 here. We see Star Trek, we see, more Star Trek and all that good stuff. But we also have this problem right here where She's Out of My League is appearing, and I haven't seen this movie, so who knows, maybe it is about Star Trek, but I have a suspicion that it's not. So what we want to do is then we want to downweight words that are all over the place. That's what's causing this problem. If I put in, a generic word, maybe it's captain, maybe it's Kirk, just by looking at the combination of that stuff isn't quite enough. So we need to add another term to our search function that downweights words that are all over the place and scattered along because they're not very important. So how you typically find to do that is through TF-IDF. And there are a host of ways of doing this that you can look up on Wikipedia. What I'm choosing is the pretty standard log version of it. Basically, we're going to, when we're adding on this new val to our return results, we're going to multiply it by an IDF score that corresponds to how many documents that appears in. Yeah, Dan.
What's TF-IDF?
Term frequency inverse document frequency. Yeah.
What does that mean?
So term frequency is this up here, where we're looking at how many times these words in combination appear inside the movies. IDF is the part where we're going to downweight the words that seem to appear everywhere. And that's mostly what it is. So if it appears in all the documents in your corpus, it's worth nothing. But if it only appears in one, it's worth a whole bunch more because that makes it very unique. So that's actually what we're doing here. So for the most part, it corresponds pretty strongly to this function up here. But all we're doing is that we're throwing an IDF term that corresponds to that downweighting right over here. and we calculate it right here. And so n is the size of the total corpus, so all our movies, and then this corresponds to the size of the hash of everywhere that word appears. And so if we do that, let's try Captain Kirk again. Oh, look at that, Star Trek's right at top. And you still see some of the other noise that we saw before, but you know, these are things that you would tweak if you were to ever implement this, because it's very specific to your use case about what words do you care about, what words do you not, and what kind of scoring should you use. What's fun about this is that you can actually, you know, start playing some games around it, like Chaos Theory Dinosaurs. Oh, Jurassic Park right at the top. Or, let's see, Wormhole Alien Message. Let's see, not quite what I was wanting. Contact, there it is. I guess that makes sense. See, it's not exact, and you have to kind of operate around it a little bit, but you do get results. And again, this is completely free text. We can try one if you guys want to shout out the search term or anything like that. Anybody? I don't know. I could type in Ruby, but I don't know if there's going to be anything inside of there. Oh, look at that. There we go. Or, you know, hacker. Superhero dancing? Yeah. So is it? So it depends on your corpus, but yeah, it's fun stuff. I mean, you can start playing games with hackers. What?
Underground worms.
Underground what?
Worms?
Worms?
We all know it's formula for here, right?
I don't know if it's actually in there, so you guys have to tell me what my results are coming back. But yeah, I mostly focus on the Star Trek. I'm a nerd. What can I say? So, but yeah, you can play in it. Again, we haven't done anything here but use base Ruby in order to generate this.
Can you look for digging? And
Now I know. Wait. Digging and what? Shoes. Again, it's highly dependent on if it's in my data or not. So.
I don't see holes.
But let's see. I don't know. You can have a lot of fun with this. Like I was looking at this Donald dance off alien wheelchair. Mac right there at top. Yeah. So you can have some fun. It's as you guys can tell, it's highly dependent on the input data that you have. This is actually in the machine learning world. This is why word to vec and all that kind of stuff is kind of suspect, because all these algorithms in NLP for the most part are highly corpus dependent. And so if you don't have the right data in there to begin with, or you don't have the right data that you didn't train with, you're not going to find the results. But if you're working on a constrained set, say if you're looking at, a list of tags, or a description of tags, or descriptions of, the only examples are coming up with things I can't talk about for NDA reasons. But yeah, in general, you can use this on a constrained corpus to really find stuff very, very quickly. So, this is cool and all, and this is stuff that you could have looked up on Wikipedia, so who cares, and where's the math, right? So one of the things that we can do is kind of look at, okay, but can we use it to find like related movies? Can we use it to make suggestions or recommendations about maybe things that we would like? And the answer is yes. So all I'm going to do is I'm going to take the description of Star Trek and I'm going to use that as my search query, and let's see what happens. So of course Star Trek comes up, but look, Star Trek Into Darkness, Star Trek Beyond, Star Trek II, The Wrath of Khan. She's out of my league again, and I think a Kirk must appear inside of there somewhere. Star Trek 6, Star Trek 5.
I looked that up.
Yeah.
The main character's name is Kirk, and then there's a dog named Captain Pickles.
Oh, gosh.
Thanks.
So, yeah, that is probably what's happening then. But if you play around with it, one of the interesting things that you can do is start to think about, oh yeah, these are all the next generation movies from Star Trek and all that stuff, if you guys are aware of that. You can see how you can populate like a queue, given that you're interested in something that you've already seen, and how you can pull up related things. And if you show enough of them, little errors like the ones that we were talking about or anything like that, the user tends to forgive you for. In fact, this is how Google gets away with a lot of stuff in general, just because of you don't know what you don't see necessarily or anything along those lines. So that's interesting, and so we can find things that are similar. We can find specific genres that way by looking at how much they relate and all that. But what if we wanted the keyword, or find the words that most relate to the documents that we're seeing? So in this case, what we're going to do is create a new hash, look at the inverted index, and only grab like the maximums, the place where the movie won out of all of them. And we're not going to do any IDF stuff. This is purely based off of count. There are ways to fix this and normalize by how long the document is. We're not going to worry about that for right now. But if we do that one was pretty fast. And if we look at keywords for hackers, we see, the names of the characters. If we look at Star Trek, we see names of the characters, Spock, all that good stuff. If we look at Jurassic Park, we'll see dinosaur names, genomes, and all that good stuff. Barbasol, interestingly, comes up. And of course, why not, right? How often does that appear inside of a movie? And so the application of this is that if you've ever worked in a company that does SEO, this is actually what you would bid on for search marketing and all that. This is actually a strategy that you would try and build off of and spend money towards in order to rank higher inside of the Google search result, because this is how Google works, at least when it's initially finding the text that it wants to link to. They have other things that they add onto the score to either promote or lower you using like page rank and other factors about your page. But when it's coming down to the keywords, when you're playing that game, this is how Google works. And so you could imagine that you design something where you look at a website and you can distill what keywords maybe they should be bidding on. And if they're not the keywords that they're currently bidding on or what they think is important, maybe they should alter the text on their page in some way in order to promote those a little bit higher.
When you say bidding, what do you mean?
So in search engine marketing, what marketers will do are put bids, dollars on certain words that they want to return in the search for. So if you see the ads that pop up at the top of Google search results, those are powered by that. There's a few things that go into the quality score, which goes into how well that word actually combines, if anyone else is bidding for those words or anything like that, those keywords. And that really determines like where you rank and certain stuff. This is how you get ahead. This is how Google makes all its money. And a huge market that exists out there in marketing tech is optimizing search engine results. This is SEO. And there's good reason for that. The ad spend, about 45% of it across all of industry is in search marketing. So if you do something that helps people do that more efficiently with the right keywords, you can make a lot of money really quickly. The problem that you kind of run into is that Google changes its algorithm and weights things a little bit differently and all that. But just as a heads up, those are from the marketing days, but that is a fun application. So another thing that you can do is take a word and return a language cloud of words that are similar. So you go out, you find the movies that are associated with that word where it appears inside the description. Then you take those movies and then you kind of work through their keywords and you see like what's kind of falling around them. And if we look up Starfleet again, now we see all these things associated with it. If we just go around to underwater, you immediately see these associations with mermaid and all that. And I mean, it seems pretty basic when we're looking at it. And yeah, it is pretty basic, but we're not using any machine learning to build these associations. the computer doesn't innately know that mermaids belong underwater or anything like that. We're just looking at the associations that come from weaving these hashes together and managing to get compelling search results out right away. Search results that are pretty good for just hacking something together in a Jupyter notebook. Now, just imagine like if you wanted to implement this in the system, you know, what you would work on. You would work on like misspellings. You would try and tweak the scores so that you get better relevant results. You would try and, you know, play around with phrases and all that. But just doing vanilla stuff like we're doing right now, we're building all these associations without any machine learning whatsoever. No TensorFlow, no carrots, no insert buzzword here. All this can be run in base Ruby. And so, you know, if we talk about, you know, where it goes, something I didn't mention either, since these are all constant time lookups, you do have some additions that happen just because of where words appear and everything like this. This is super fast, super duper fast. You might run into some spacing problems, and that's where you start replacing these hashes with Redis, and you can pipeline things appropriately inside of Redis so that you're limiting your calls, and you can do things with Z underscore and all that stuff to do some of the math for you. But you can make these things extraordinarily fast. So I did feel like I needed to say, you know, where's the math and blah, blah, blah. I thought this was about math hacking. We did a little bit of logarithms before, but when you look at how we're weaving these keys together, what that corresponds to is matrix math. If you remember your linear algebra and all that, that's actually what we're doing. And when you make that insight, you can start playing around with, you know, more advanced concepts of like projection and singular value decomposition or eigenvalue decomposition in order to build like true proper topics. This is actually how PageRank itself works by taking advantage of that. They're just looking at links between websites. Now we have another way to do PageRank, just working off of text directly, which is kind of cool. So, you know, if you do implement something like this, and this might be slightly relevant for some of the people in this room, you know, some of the questions that you want to ask yourself is, how do you handle spelling mistakes? You know, and how do you avoid using a package? You can use a package, but, you know, it's good to actually know how to solve these problems. And, you know, could you split up the words into n-grams? Could you then do TF-IDF on top of that and find the most likely cause? Can you play games with how you vectorize things in a certain way? You know, how could you improve the inverted index so that Starship Enterprise is way more valuable than Starship and Enterprise by itself? Or Captain Kirk, as a phrase, is way more valuable rather than Captain or Kirk, so that we avoid the problem that we were running before. The natural tendency, which is probably the right one, is that you do some n-gramming over your arrays or something of that nature and grab all that stuff, but then you have to start tweaking with scores a little bit. But this is all extremely doable. And again, it's all with base Ruby so far. And then another question is to always ask, you know, how do you actually implement this in production, and how could this fit into some of the models that you're building, and how would everything interact with one another? And with it being so simple, I imagine that it would be pretty quick. I mean, you guys are the experts, but I could imagine. This is what, maybe 20, I don't know. Let's just say 60 lines of code, and we have an effective search engine that can make all sorts of associations, that can find things across generic text, that can kind of operate and find keywords that maybe we should bid on, or topics that we care about, and it's all on base Ruby. So yeah, so I guess you can do a little bit of data science in Ruby. But yeah, that's about all I have. It was definitely fun learning this, I have to say. Those implicit returns, oh my gosh. I mean, holy cow, that was something. And
What about
you know,
unless? How many days did it take to feel comfortable?
oh, I'm still not comfortable. I mean, I did this like a couple days ago. I started searching for it and all that. I'm still used to it, if not.
Yeah.
So yeah.
Using unless is
Yeah. So any questions at all? I can give other examples too. It just doesn't have to be this. I'll just start here and work my way around. Yeah.
I was curious if you'd ever done work with things that do like summaries or like the abstract from
Yeah.
a large document and how that might work?
Yeah. So when I was at Demand Jump, I actually created a module that had a method on it called TLDR. We had a way of distilling documents down to keywords. Then we use those keywords to search for lines inside the text, and we could construct a summary just directly from them. We didn't use the keywording thing that we were using here. The math hack that we actually used in order to construct that was basically, have you ever noticed how popular like short words are? Like the word the, it appears all the time. A, and, words like that appear all the time inside of language. And it follows a general pattern called as if distribution. If you look for words that are falling out of that pattern, you're going to find the words that the author went out of their way to say, right? And so if you're doing that, you can keyword, and then you just look at where those words appear, and then you can pull a summary together for it. And what's really cool about that is it works in every language, which is awesome. You pull some, because it's the same thing. If you've ever learned another language, in German, all the common words are the short words. In Spanish, all the common words are the short words. And you just take advantage of that hack, and you can extract everything in every language. I actually have another slideshow that I can show you, like the network that comes out of it, but I'm a little nervous about messing with the screen, if I'm honest with you. So, yeah, Grayson.
Yeah, so here, when you were ranking movies against one another, you used the Wikipedia description, correct?
Yeah.
Okay. What would you do? What sort of strategy would you apply if you had a description that wasn't, several hundred words, but was instead like 10 words or something like that? Would you still apply the same strategy?
Yeah, so it takes experimentation, to be honest with you. It depends on the kind of text that you have and what goes into it. But if you have just a bunch of tags that are associated with a certain concept or anything like that, the optimal way to approach it is probably doing something called min hashing. It's where it's basically a way to efficiently do Jacquard similarity about how many things are together versus how many things are there all together. How many things intersect versus the union of two sets. And what's really neat about that is that you can implement it like we did the TF thing once you get your essential tags down, which is really, really cool. And yeah, you can operate extremely fast, and it's also fuzzy, so if you were to search just one term, you would get everywhere where that appeared, but if you search two, you could set certain thresholds and rank them according to that score, and it would be really, really awesome. I had a question here.
Yeah, I was curious if you thought this would be a practical strategy if your underlying data set, your dictionary, was actually changing constantly.
So that actually depends. If you are getting constant new data and everything like that, if you set it up correctly, you can make this scale very nicely. There's a few things that you have to keep track of. So first, on ingestion, when you're actually bringing in a website, let's say that you're just crawling, you're going to immediately set up your insertion. That's what we were doing here with the clean and split. You would just insert that into Redis, doing a Z ad or something like that, in order to actually update all your terms and get your term counts out. The one extra thing that you will need to do is keep track of how many documents that you have. That's where this N comes in on the TF-IDF side, and that's where you start playing games. If you're working in Redis, this is what I did at Demand Jump. You keep both sides. You keep the feed forward index so that you have every tag that that website is associated with, but then you also have the inverted index where you have the tag to the individual documents. And then all you need to do is just look at the count of what's inside your feed forward network, and that can rebalance everything as you ingest new stuff. Yeah. Any other questions? Sorry, my brain starts thinking about math all of a sudden, and I get going, and I can't speak all of a sudden. Any other questions? Yeah.
Is this all open source or is it proprietary?
You guys can use all of this if you want it. I mean, you can look at it on Wikipedia, but feel free. You can make this code way nicer. I guarantee it. So yeah, feel free to use it as much as you want. Yes.
Other question. With like academic papers now, like a lot of like science stuff where English is the language being used, but not always the native language of the author, where it becomes like easy to like when you notice like these grammar like issues, and then how you talked about ignoring the grammar to score the keywords and stuff. Do you think you could do use that technique to fix the grammar in the papers?
Well, to be honest with you, I don't know, but possibly yes. Going back to the thing that I was talking about earlier, there's a certain flow, a certain structure that we all know from grammar. Our brains have just figured it out as we've learned to talk and learned to write and all that good stuff. And kind of pairing that with something maybe like a Markov bot or something like that could probably help you out solving that problem. It could be really cool. And you could imagine that you'd have all the text that's kind of leading up to it, and then you had a hash of everywhere that it could go next. And if the word that they type in doesn't correspond to something inside that hash, it's like, oh, we got a problem. Or if it doesn't appear as often as you would expect it to. But I mean, there's some gotchas there. You don't want the most generic possible sentences coming out of that. And so you would just have to work on it, work that out and see how it worked in user testing and all that. Any other questions?
Playing devil's advocate for the record.
Uh-huh.
Zach, imagine I'm one of your clients who has read just enough about machine learning to have a dangerous conversation with you.
Yeah.
And I say, well, it seems to me that this is like a classification problem in machine learning, right? Like why wouldn't you rephrase this as a classification problem and write a machine learning algorithm to solve this problem?
That is beautiful. Let's consider about how we would actually do that. So if you have a neural network, more than likely you're going to do it with a multi-layered perceptron. You might try and do it with some other fancy technique, maybe using a LSTM or something like that. But in general, let's just take our multi-layered perceptron. Now, that is just a fancy word for layers of neurons that give you a yes or no, just depending on what's coming out. Now, what we would input into that is your query term, right? And then what we would get is like a probability of it's this movie or that movie. That's in general how those things get delivered. Let's think about how we would have to train them. So I would have to train each of these into that network over and over again. I would have to worry about how the error is working, worry about if it would actually balance, if it would actually converge. And if I ever added a new movie, I would have to restart all over again. And it could possibly destroy the network itself just because we'll have way too much information that we're trying to extract from it, from the same sort of inputs. And on top of it too, the hardware that you usually have to use for big neural networks and all that kind of stuff is rather expensive, even when you're working on AWS and all that, because you guys need GPUs and all that good stuff. Meanwhile, I get the same results or even better results using base Ruby, using nothing but hashes. And so that's usually how I would phrase that with a client, because there's no denying it. Neural networks and machine learning do really awesome stuff, but it's never it never should be where you start. It should be necessitated by what is the problem demanding? What does the data say about itself? Because machine learning algorithms run wild, do really awful stuff. There was a time not too long ago where someone was trying to use neural networks in order to predict recidivism, when people would come back after leaving prison, back to prison because they reoffended or something like that. And what that neural network actually ended up doing, it became extremely racist. Extremely, extremely racist, because they just applied it blindly. They didn't take into any effects, any kind of social factors or anything like that. They just figured out how to vectorize it, and then they applied it, and it turned out that the network ended up being extremely racist. And the thing is that the people who made that algorithm, they weren't racist. The problem is that once these neurons get all trained, and you have the weights that happen in between them and everything that goes with it, no one in the world can tell you how the network is working any longer. You can work out the math, you can look at the code, you can look at the weights, but you don't know how they all link together. And so you never quite know if you're biasing the data in a certain way, unless it is like honed down and it's appropriate for the problem. So that's why I say, let's at least not start there. Does any other questions about neural networks or anything? I can talk all day about that stuff. So yes.
I'm curious if your strategy scales with
Strategy for
well, the one you went over already. Does that scale very well?
the neural network to do the movie detection,
No,
or
no, just the hash.
yeah. So how this you will have to start playing some tricks about, am I filling up the hash space too much, and you might end up with collisions or something like that. But this inverted index and everything. This is how Google runs. If you think about all the requests and everything that they're doing, they have to have something that's that quick, that they know exactly where to look in their database in order to get the results out. Because otherwise they wouldn't be able to service the results as fast as they were doing it. These key value stores are extremely dependable. It's remarkable. You see them implemented almost everywhere too. I mean, Redis is a good example. But if you look at Postgres and if you look at indexing options, there's an option to use a hash, and this is essentially what it's doing behind the scenes.
Would be pretty much being memory bound.
Yeah, absolutely. Yeah, and Redis for that matter too. But yeah. Any other questions?